Welcome to the Explainer. So imagine you're walking into a hospital room, right? And you see this massive, honestly kind of intimidating MRI scanner. I mean, it literally feels like you've just stepped onto a sci-fi movie set. You've got this giant humming tunnel taking up the entire room. But here's the really fascinating mystery we're going to unpack today. How does this colossal machine actually work to reveal the secrets hidden right beneath your skin? Think about it for a second. There are absolutely no cameras inside that tube. There's no bright flash of light. In fact, it's completely dark in there. Yet somehow it can map out your soft tissues, your muscles, and your internal organs with just unbelievable pinpoint precision. So how does a machine with absolutely no eyes actually see inside you? Well, the surprising truth is, it doesn't see at all. It listens. Okay, let's dive into this. When you think about this intimidating piece of hospital equipment, your first instinct might be to picture it as a giant camera. But honestly, you should actually think of this entire massive structure as an incredibly sophisticated, highly sensitive radio receiver. It's totally designed to pick up these impossibly faint signals coming from your own body. But to do that, to actually listen to your biology, it needs some serious electrical engineering magic to power the whole shebang. Right behind that sleek plastic casing of the MRI are two totally unsung electrical engineering heroes that actually make this medical magic possible. Meet the capacitor and the inductor. Without these two completely invisible components working behind the scenes, there is zero listening, there's no signal, and there is absolutely no medical image. Let's look at our first hero, the capacitor. I want you to think of the capacitor as your ultimate energy reservoir. Picture a fire station, right? It's got this massive water tank. It stores water quietly until an emergency hits, and then boom, when it's needed, it releases it instantly in this incredibly powerful stream. That is exactly what a capacitor does with electrical energy. It stores it all up, and when the medical imaging system needs a sudden pulse of power, the capacitor acts as an energy launcher. It releases everything in a massive, instantaneous burst. Without it, the machine would literally be way too slow and unstable to even function. And just to give you an idea of the sheer scale of the energy we're talking about here, we are not just talking about a tiny spark. The sources point out that the gradient amplifiers powering these MRI systems can generate up to 8.1 MVA. That's megavolt amperes of apparent power. To put that wild number into perspective, that is roughly the horsepower of a dozen Formula One racing cars, all packed into the machine's power system. It generates so much heat in mere fractions of a second that it requires intense, state-of-the-art water cooling just to keep the system from totally overheating. That is a massive amount of sudden power that needs to be managed. Which brings us right to our second character, the inductor. If the capacitor is our explosive energy launcher, well, the inductor is the magnetic guardian. Imagine a really heavy, solid spinning wheel. If you try to stop it suddenly, it resists. If you try to speed it up instantly, it resists again. It aggressively wants to just maintain its current state. And an inductor does exactly this, but with electrical current. It's basically a coil of wire that stores energy in a magnetic field, and it stubbornly resists any sudden changes in the current. In an MRI machine, this stability is literally everything, because even the tiniest electrical disturbance could completely ruin the image. So consider the dynamic tension between these two components. It's this beautiful engineering rivalry. On one side, the capacitor, your instant burst, your energy launcher. And on the other side, the inductor, resisting change, acting as the magnetic stabilizer. They seem like complete opposites, right? One wants to dump energy instantly, the other wants to prevent sudden changes at all costs. But the real magic happens when you force these two opposing forces to work together. And the concept of a resonant receiver circuit brilliantly illustrates how they actually connect in real science. In this kind of setup, the C stands for our capacitors, which handle the tuning. And the L stands for our inductors. When you wire a capacitor and an inductor together in a closed loop, they actually start to kind of talk to each other. They form what is called an LC circuit. The energy flows between them in this continuous, perfect cycle. Step 1, the capacitor releases its massive burst of energy. Step 2, the inductor absorbs it, resisting that huge surge and storing it smoothly in its magnetic field. Step 3, the inductor pushes that energy back out. And step 4, the capacitor absorbs and restores it. Think of a playground swing. You push it forward, it swings up, stops for just a tiny fraction of a second, and swings naturally right back down. This continuous back and forth energy flow creates a perfectly natural rhythm. It's what we call an oscillation. Let's move to and see how this builds into the actual medical procedure. Now that we've got this perfectly rhythmic listening device, what exactly is it listening to? Well, the target is the human body. specifically the millions and millions of hydrogen atoms that make up the water and lipid molecules inside of you. Your body is basically a symphony of tiny magnetic protons just waiting for the right machine to hear them. I absolutely love this analogy from our sources to visualize what happens next. When you slide into the MRI, the machine surrounds you with a static magnetic field that is, frankly, staggering. We're talking typically more than 10,000 times stronger than the Earth's natural magnetic field. This massive force completely aligns your protons. As the source describes it, the spins of the protons in your body's molecules line up, facing the exact same direction, like a marching band practicing on a football field. They're all perfectly at attention. But to get a marching band to make some noise, we have to cause a disruption. So the machine applies a highly specific short radio frequency pulse. Imagine a stray football suddenly launched right into the middle of that perfectly aligned marching band. The protons get this quantum nudge, and they immediately break formation. But as soon as that radio signal stops, the protons scramble to realign themselves with that giant magnet. And here is the absolute secret to MRI. In the process of getting back into formation, they emit a very weak amount of measurable energy. They actually broadcast a tiny radio signal. But wait, how does the machine single out that tiny whisper of a signal over all the massive electrical noise happening inside a bustling hospital? That's where the Larmor frequency comes in. This is the exact resonance frequency proportional to the magnetic field strength. It acts as the secret language of the MRI. For a standard 1.5 Tesla clinical scanner, that frequency is precisely 63.9, or roughly 64 megahertz. This is the exact pitch, the literal mathematical note that your hydrogen protons use to broadcast their tiny radio signals. So the crucial point is that LC circuit we built earlier out of capacitors and inductors, it acts just like a precise radio dial. It's tuned mathematically to resonate at that exact 64 megahertz frequency. Think of tuning an old school car radio, right? If you're even slightly off frequency, you just get ambient noise, static, and disturbance. But when you dial it into the exact correct resonance frequency, bam, you get one crystal clear station. The MRI's receiver circuit acts as this precise filter, blocking out all the static and amplifying only the secret language of your hydrogen atoms. Let's bring this all together to really lock in what we've learned today. We've got the capacitor, acting as our explosive energy launcher. We have the inductor, acting as our steadfast magnetic stabilizer. Together, they create the LC circuit, which is this perfect, oscillating rhythm system. All of this unites to turn the MRI into an incredibly powerful, perfectly tuned machine that simply listens. A computer then takes these super faint rhythmic signals and beautifully rebuilds them into the detailed 3D images that literally save lives every single day. So the very next time you look at one of these massive, honestly intimidating machines, remember this. It's not just a big camera. It is conducting a quantum orchestra using the totally invisible heroes of electrical engineering, which really leaves us with a fascinating thought to ponder. What other invisible symphonies are playing inside us right now, just waiting for the right machine to listen? Thank you so much for joining me on this explainer, and keep staying curious.